The subject of this lecture is chemical vapor deposition, as it is being used for the production of very large scale integrated circuits. I have an outline here which lists the various subjects I would like to cover. We'll have a brief introduction to CVD in general, then go to fundamental properties, fundamental principles of CVD, and proceed to CVD processes and technology, and CVD reactor systems. So this, up to number 4, will be covered in the first half of this lecture, and then the second part will continue with deposition of dielectric materials, deposition of semiconductors, and finally deposition of conductor layers. Let us start with a definition of CVD. As the name implies, chemical vapor deposition is a chemical process. And again, as the name implies, it occurs in the vapor phase. However, the critical processes actually take place on the surface of the substrate. So more correctly, the desirable types of reactions we like to have happen on the surface of the substrate material. As far as differences from other processes are concerned, here, for example, we have physical deposition processes like sputtering, evaporation, and so on, in which case no change of the material itself takes place. Whereas in CVD, we have in all cases a transformation of a material into another material by a chemical process. Historically, CVD has been around for a long time, but only until the advent of the semiconductor industry has CVD become one of the major methods of film preparation. And I could say nowadays, without CVD, the whole era of computer technology would be hard to think about without it, because all of the, or the large majority of the films are deposited by chemical vapor deposition processes for the production of integrated circuit chips and VLSI in particular. In general, perhaps CVD has been on for 100 years or more, but as I said, the importance has been started to be apparent in the 1950s, and most recently, of course, with the advent of VLSI technology, sophistication of the process has been still further developed. Now, the types of deposits we can obtain by CVD cover a very wide range, as we will see. They can go from dielectrics to semiconductors, metals, and it is a very large variety. Essentially, almost any type of inorganic material can be deposited by CVD methods. The examples we will see in a moment, so we'll skip to the next point of the advantages. Why would we want to use CVD? CVD is primarily a process where we can deposit materials at very low temperatures compared to their melting point, shall we say. So it is a very versatile method which allows the synthesis of many different types of compositions fairly readily and at low temperature. The disadvantage perhaps with CVD is that we are restricted to materials that are available that can be introduced into the gas phase and can be reacted. That is one limitation. Another drawback perhaps is the fact that we have to use in many cases toxic and materials which are corrosive, poisonous, and so on. So we have to have a careful control over those processes. In order to know what's happening really during the process, we have to do a vapor phase analysis. The simple analysis of the end product, of course, gives us some clues of what may happen during the process, but unless we do a in situ analysis using mass spectroscopy and Raman spectroscopy, optical techniques, and so on, we don't really know what is happening during the process itself. So instrumentation has been perfected in recent years to achieve that kind of understanding. The reaction chemistry we'll discuss shortly is essentially similar to or the same as normal inorganic chemistry, except everything happens in the gas phase. Now, let's have a look at the types of materials we use in microelectronics and VLSI applications and point out what can be done. Actually, just about everything that's shown here That is, the insulators, as well as the semiconductors, conductors, and superconductors, and even magnetics, can be produced by CVD methods. Under the insulators, the most important one, of course, is silicon dioxide. Silicon nitride is perhaps next, and aluminum oxide, and the various silicate glasses, such as phosphosilicate glass, the PSG, and various other types are used for doping applications, for example. All of those can be very readily prepared by CVD methods. Under the semiconductors, the elemental semiconductors, silicon and germanium, as well as the gallium arsenide, gallium phosphide, and a host of other alloy type of semiconductors are being deposited by CVD techniques. The conductors generally are preferably done by physical methods of deposition, except the refractory metals. In this case, tungsten, molybdenum, and those are preferably done by the CVD method. The superconductors and magnetics, I'm just listing those for completeness, but they again are being prepared by CVD. Let's have a look at some of the basic aspects of CVD reactions as listed in this table. First of all, in number A, the vapor pressure or volatility requirements are such that they should be high for the reactants in order to transport them to the site of the reaction, that is, into the reactant, to the surface. They should be high for side products to be eliminated, and of course they should be low for the product to remain, which means gases in most cases in all cases are preferable, because you don't have a problem with the vapor pressure and so on, whereas if you have a liquid, you have to vaporize the liquid first and produce sufficient vapor, heat them, for example, to produce sufficient vapor pressure to get a quantity necessary into the reactor itself. If it's a solid, it's even more difficult, because now you have to melt the solid to a liquid and from there transport the vapor of that liquid through a heated conducting system into the reactor, which is sometimes difficult to do, but perhaps necessary if there's no other choice. Now, the reaction energy under B, the types of reaction energy can be thermal energy, simple heating, as in most chemical reactions is done, or it can be an electric discharge, a plasma glow discharge, for example, or it can be electromagnetic radiation, such as electron flux, or it could be laser radiation or photon radiation of any type. So all of those are means to get the reaction going. Under C, the nucleation and film growth, there's two major aspects, namely homogeneous reactions, which occur uniformly in the gas phase, and those are the ones we don't want, because they lead, in most cases, to gas phase nucleation of particles. The second type is the heterogeneous type of reaction, which is a selective type that proceeds on the substrate surface, and of course that is the one we wish to control and wish to obtain. We'll see more about those two reactions in a short few minutes. Finally, the effect of temperature. Generally, a temperature increase produces a higher growth rate if the reaction is endothermic, as most chemical reactions would be. The greater density of the deposit also results from the increased energy or increased heating. And another additional effect is the improved crystallinity. So in epitaxy, for example, where we do want a very good, perfect single crystal material, we have to go to a high enough temperature to achieve this. On the other hand, we also have the negative problems of the greater interdiffusion, the diffusion of impurities and so on, as we increase the temperature. Okay, now let's look at some of the fundamental principles involved in CVD. They are listed here, starting off with the reaction chemistry. We will look at a few examples of those in a moment. The reaction chemistry, as I said, is essentially straightforward inorganic physical chemistry without any particular problems, except that everything takes place in the gas phase. We have the gas-phase homogeneous reactions I just mentioned, and the surface heterogeneous reactions, which are the ones we really want. we can really say that the CVD method is more of a surface reaction method than a vapor phase reaction, because what we really do want is the heterogeneous type of reaction which does occur at the surface of the substrate. The fourth thing is thermodynamics, and we will have a brief look at some thermodynamic considerations and go on to kinetics and energy, mass, and momentum transfer. All of those are very important in the reactions, in the reactor design, and in maintaining conditions that lead to optimum results. The heat transfer is another consideration. The heat transfer from the substrate or from the reactor plate to the substrate, and also from the into the gaseous reactants of the system. The number 8 here, the flow dynamics, is another consideration which we have to consider, as well as the pressure effects. That is, the pressure, of course, does have a pronounced, just like temperature has a pronounced influence on the deposition conditions. The nucleation phenomena are an aspect which, a whole separate type of aspect, which is a subcategory of the whole CVD theory, so to speak. And there's various aspects of the film growth, that is, how the film deposits on the substrates as a function of environmental parameters. And finally, the gas-phase composition analysis. Now, as I mentioned before, of course, each one of these could be a separate lecture, and to do justice to each of these, it should be, but because of the time requirements, we cannot really cover more than the first 4, perhaps, very briefly, or 5, up to the kinetics. I will show you some examples of these. As far as chemistry is concerned, we can essentially classify the various types of reactions taking place by CVD into the ones listed here. To begin with, pyrolysis. Pyrolysis is really a process which is thermal decomposition of a material without any other interaction. In other words, we simply heat, such as silane, we heat it, and we obtain silicon and hydrogen as a byproduct. The next one would be reduction, used frequently for the preparation of metals. In this case, we have, for example, tungsten hexafluoride with hydrogen producing tungsten and HF as a byproduct. The next one listed here is oxidation, very important reaction, which again, using silane as an example, we can see that the silane with nitrous oxide, in this case, forms SiO2, nitrogen, and water vapor. Hydrolysis is shown here as an example using the aluminum chloride in the vapor phase with CO2 and hydrogen to form aluminum oxide and HCl and CO. Nitride formation is indicated here as an example. Here we have silane and ammonia forming silicon nitride and hydrogen as a byproduct. And of course, all of these reactions are done under specific conditions of temperature, pressure, and so on. Now, this one would be done, for example, at the temperature of 800 degrees centigrade if we use LPCVD. To give you a feel for that. Now, carbide formation is shown down here using titanium tetrachloride and methane to form titanium carbide layers and HCl. Disproportionation is another type of reaction. In this case, we have germanium diiodide forming germanium and germanium tetraiodide, depending on the temperature of the system. It can be a reversible reaction. About the organometallic reactions, which have become much more important recently for the synthesis of compounds and semiconductors. Here we have trimethyl gallium reacting with arsine to produce gallium arsenide and methane. And finally, transport reactions, where we transport one material with a suitable transporting agent, such as HCl or water vapor, into another. And here I have gallium arsenide shown with HCl to produce various species of arsenic and gallium chloride. Again, this is a reversible reaction and will depend on the temperature of the system, which way it will proceed. Let's have a little closer look at the important homogeneous versus heterogeneous type of reactions using a very simple example, in this case the silane pyrolysis to silicon and hydrogen. We have essentially two types of possibilities. We have the gas phase reaction or we have the surface reaction. In the gas phase, what happens is silane dissociates to SiH2 and hydrogen, which then reacts further with silane to produce disilane or Si2H6. Alternatively, we have a build-up into higher silanes as shown down here to silane silicon Si3H8. Now, all of these reactions occur in the gas phase, and there are many more intermediate steps. On the surface, on the other hand, we have silane depositing directly as silicon, elemental silicon and hydrogen, in all cases, whether it is silane or whether it is disilane or whether it is the more complex type. So these are the types of reactions, of course, which we would like to have, namely the deposition of film on the surface. Incidentally, of course, in all of this, we are really concerned with the deposition of thin films rather than anything else. And thin films meaning films in the range of a few hundred to a few thousand angstroms up to perhaps a micron or so for VLSI type applications. However, CVD, of course, can be used for production of bulk materials just as well. I just would like to point that out. It is not restricted to this. But the technology has been perfected to the greatest degree for thin film deposition as used in VLSI. And okay, of course, similar types of reactions can be predicted or postulated for other types of materials, such as gallium arsenide. Okay, let's have a look at some of the thermodynamics here. Thermodynamics, of course, is important to predict the feasibility of a reaction to occur and to see the feasibility, establishing the feasibility of the reaction to begin with. And if we go down the list here, I try to point out some of the important things. Again, I cannot go into any great details, but let's just go down the list here and see what essentially we have to deal with. Now, the free energy of formation, or the delta GF sub F of a chemical species, has to be known as a starting point. And has to be known for both the vapor species and the condensed constituents of the system. So this is the starting point we need to begin any type of calculation. Now, number 3, down here, the free energy of reaction, or the delta G sub R, can then be calculated if the delta G sub F values are known. The delta or the G sub F is the sum of the products minus the G sub F of the sum of the reactants, can now be utilized. In number 4, the equilibrium constant K sub P of the reaction is related to the partial pressure of the system as shown here. The K sub P essentially equals the product of the pressures of the substances produced to the A power divided by the product of the reactant pressures divided to the B power. And of course, A and B are the coefficients of each substance in the chemical reaction equation, the summary equation, as we normally do in physical chemistry. In number 5, the free energy of reaction, the delta G sub R, and the equilibrium constant K sub P are related by the equation shown. If we consider in point 6 a general reaction, as a general CVD reaction, that will be represented by the formula given here, by the equation given here, where A sub G, that is a gaseous species of A plus a species of reactant B, and so on, to give us a reaction product M sub S and N sub G, and so on. But however, where only one of the components is a solid. If that is the case, we now can we can now calculate by means of the Van 't Hoff expression which relates the K sub P, the T, that is the absolute temperature, and the delta H by the equation shown. And the delta H, incidentally, there is the enthalpy of reaction, which can be positive or negative, which again can be calculated from the delta G sub F plus the delta T times S, S being the entropy of formation. And of course, as we all remember, the positive values of delta H will indicate an endothermic reaction type, where the negative value would be classified as an exothermic reaction type. The thermodynamic calculations assume a reaction equilibrium, and it also assumes a thermodynamic availability to thermodynamic data, which is not always the case. The equilibrium, of course, is another thing. The CVD reactions are rarely or hardly ever in a full equilibrium, so it is quite an assumption one has to make. And however, it does give us an initial starting point to see whether a reaction is feasible or to what extent one can expect it to run. Okay, so far for the thermodynamics in general. Now let's look at a specific example, a very simple example where how we can utilize the type of calculations I have just shown. And this will be for the selection of a reactor type using the Van 't Hoff equation we had just discussed. In this case, let's look at A here, where let us assume, or let us start and say that the delta H would be negative and the absolute temperature is increasing. Then the sequence of events listed on the A, B, C, and so on is taking place. The K sub P decreases, reaction shifts to the left of the equation, deposit M sub S decreases, and the reaction would be considered exothermic. Therefore, a hot wall reactor will be needed to prevent deposition on the walls, because if it would be a hot wall reactor being one like a resistance heater type of CVD system, if it would be the opposite, that is the wall would be water cooled, for example, then the opposite will take place. We would have deposition occurring at the reactor wall rather than on the substrate. Now, an example is shown here of this type of reaction, namely epitaxy of germanium by disproportionation, where we have germanium diiodide going into germanium and germanium tetraiodide with a delta H of minus 37 kilocalories per mole. Now, if we look at a second example with a very similar type of equation shown down here, again, epitaxy of germanium using by reduction, in this case, using germanium tetrachloride, things are exactly opposite. In this case, let us assume here now delta H is positive and the absolute temperature is increasing. And what then happens is the exact opposite type of sequence text would be holding here in this case of what we discussed above. As a result, we would have to use a cold wall reactor because of the reaction being endothermic now. We have to use a cold wall reactor with an RF heated substrate in order to have a selectively heated area rather than having everything else hot. So the example here now shows us that we wind up with actually this reaction now takes place with a delta H of positive 34 kilocalories per mole. Absolute value being very similar to up here, but opposite in its sign. Now, so far for the a few thermodynamic conservations. Now let's look at the kinetics, which is really the other part that is very important, which will tell us how the reaction will proceed. That is assuming it will proceed, to what extent it will take place. And here we have essentially 5 types of steps. The first one here is mass transport of the reactions to the surface of the substrate. Is the first thing that has to occur. Then the adsorption of the reactant species on the substrate surface. And then number 3, the interaction, which includes surface diffusion on the substrate itself, and then number 4, the desorption of the side products, and finally the mass transport of the product gases away from the substrate. Now, one exception is the epitaxy, because it includes or involves epitaxial nucleation type phenomena that does not follow these steps. But other than that, all CVD reactions will follow this type of sequence. And of course, the slowest sequence, the slowest step will determine the all-over sequence of the total reaction. If we look at another aspect of kinetics here, which is the temperature dependence, we look at number 2, the nature of the rate controlling step, which will change with temperature. Essentially, we have 2 types. One listed under A, which is at a lower temperature, namely this one here, which is essentially a surface process that is controlled by exponential temperature dependence. And a higher temperature type of reaction, one that takes place at a higher temperature, which is usually diffusion controlled, a diffusion type process, and which has a mild temperature dependence, as we will see on the next slide here. This is a typical presentation of a type of reactions we are talking about here. We have the growth rate on the left side as a function of absolute temperature for the deposition of silicon from various source gases, silane on the top, and the various types of chlorosilanes. And you can see that, first of all, the absolute deposition rates vary, but the slopes are essentially very similar, meaning the activation energy also is very similar for each of these reactions. However, we definitely see 2 types of curves, a very steep one going from the right to the left, and in this case, that's the lower temperature type process, which has an exponential temperature dependence, very steep, very sensitive to temperature, then reaches a knee on the upper part of the curves and levels off. So all of the curves then level off at a higher temperature end, which are the diffusion type processes, which are not influenced to any great degree by temperature. So that is a very general type of behavior that holds for most of the type of processes. Now, another aspect we should consider is the LPCVD system. That is the LPCVD, the low pressure CVD, as compared to atmospheric pressure CVD. And I have attempted here to put this into words, and also afterwards we'll have a look at the mathematical equations that govern the processes of this type. Let's go down this list here very briefly and see, starting with A, key parameters for achieving any type of CVD film is uniformity. Now, the control of uniformity is based essentially on the number 1 and 2, the mass transfer rate of the reactant gases to the substrate surface that has to be controlled, and then the surface reaction rate of those gases once they have arrived at the surface and interact. Now, in normal pressure CVD or atmospheric pressure CVD, the mass transfer and surface reaction rates are essentially the same, or at least in the same order of magnitude. Now, if the substrate lays side by side in a reaction tube for good uniformity, as it used to be done before the LPCVD type of processing was developed, it is necessary, in order to get good uniformity, to lay the substrate side by side flat in the tube. If we would stand them up, as we now do in LPCVD, but would use the normal pressure CVD, for vertical closed-space substrates, the mass transfer rate to the surface would be very much smaller than the surface reaction rate and cause, as a result, an edge buildup. In other words, we could not operate at atmospheric pressure with vertical closed-space substrate wafers. In LPCVD, which is shown here, the mass transfer rate is greatly enhanced, allowing the surface reaction rate to control the deposition. Now, vertical closed space substrates are uniformly coated as a result, but it still perhaps isn't clear why. Now let's examine this in a little more detail under D. And here we show that the mass transfer of gases involves the rate controlling diffusion across a slow moving boundary layer, which is always present above the substrate itself. Now this boundary layer is the limiting factor here, and but in any case, that is a very important aspect, the transfer of the gases through this stagnant layer of a boundary layer above the surface. Under E, the mass transfer rate now depends on a number of things here, namely the reactant concentration, the boundary layer thickness, and the diffusivity of the reactant gas or gas mixture through that layer. And the surface reaction rate, on the other hand, depends on the reactant concentration and the temperature only. Now, if you lower the pressure by a factor of 1,000, let's say from atmospheric 760, let's say 1,000-fold, what happens is the diffusivity increases by 1,000, and as a second consequence, the laminar boundary layer increases by a factor of 10, and the mass transfer therefore increases by a factor of 100 because of these 1,010 factors here. Of course, the mean free path is increased as a result, and as a result of all this, the uniformity is greatly increased, the uniformity of the film deposit. Another negative aspect, of course, is that the deposition rate is decreased simply because we have less material available at low pressures than you would have under atmospheric conditions. Now, to achieve optimal LPCVD conditions in practice, one would have to do a number of things besides lowering the pressure. Increase the reactant concentration, which is one thing, to get a high partial pressure of the reactant itself, and eliminating the diluent gases to achieve this, and which is, of course, economically considering a desirable thing. Again, we can do with fewer reactants and less diluent gas. And finally, we have to select the best temperature, which may involve some ramping of the temperature profile to get a profile which is conducive to uniform film deposition. That is, we may have to ramp the end of the downstream end of the reactor tube by 5 or 10 or so degrees to compensate for any depletion effects. Now, the substrate spacing is another important aspect. That is the wafer-to-wafer spacing and also the flow velocity. All of those factors have to be optimized to get the best film uniformity. And finally, we have to adapt the reactor configuration itself as far as gas distribution is concerned to give us the best uniformity, especially at a low temperature end. This is an important consideration where we have to distribute the gas as uniformly as we can. Now, if we look very briefly at the low pressure CVD compared with atmospheric pressure CVD, essentially what I just went through, but putting it into more concise terms perhaps, in this case looking at the numerical values, and we start off with atmospheric pressure CVD at let's say 1,000 torr pressure, and what happens as we then decrease the pressure to 1 torr, we can see what happens to the various factors here, the change of diffusivity from 1 to 1,000 here, and the velocity change, density change, and also the change of the Reynolds number being defined down here in this equation. And we can also see the thickness of the boundary layer changing from a value of, say, 1 to a value of 3 to 10. In other words, the thickness of the layer actually increases because the boundary layer, the stagnant layer, becomes diluted out. So you have a expansion of that layer. However, the diffusivity changes to a very large extent because the diffusivity now through that layer because it is expanded, is greatly different from what we have under atmospheric pressure conditions for the various gas species. And of course, the boundary layer thickness is defined in this equation over here, where the Reynolds number is part of the aspect of the expression. The terms are detailed down here to specify exactly what is meant by the various terms. Okay. We are still considering various aspects of the more fundamental type aspects of CVD. And one thing we have to consider here next is the plasma. CVD, there are various forms of CVD, and even though plasma generally might be considered a separate subject, however, plasma CVD reactions are part of the all-over CVD processes and should be considered as such. So let us have a quick look here at the types of plasmas and reactions that occur. First of all, by definition, a plasma is a partially ionized gas which is composed of the ions, electrons, and neutral species that are available, and it can be generated either by high temperatures or by strong electric or magnetic fields, as indicated here. Now, in CVD, in plasma CVD, it's really CVD taking place in a plasma produced in a gaseous electric discharge. And here we have electrons which essentially gain energy from impulsed electric fields, transfer that energy kinetically to reactant molecules, and in the process produce a large variety of free radicals, atoms, metastable species, excited molecules, photons, and so on, which then interact and form film materials. Because of the great variety of reactants available, you have also a large possibility of film formation of various types, which can be an advantage, of course, but it also is difficult to control them in a practical sense out in the field to really produce a composition of well-known characterized behavior and repeatedly doing so. As far as the low pressure glow discharges are concerned, and those are the ones, of course, we are really using. I have indicated here a number of points which are important in creating the glow discharges. Essentially, the perhaps most important aspect is shown down here. The electron energies that are in a range of 1 to 12 electron volts in the pressure range of 10 to the minus 3 to 10 torr, and electron densities in the range of 10 to the 9th to 10 to the 12th per cubic centimeter. Now, the electron temperature over gas temperature ratio is in the range of 10 to 100. Now, the high electron temperature is really the key to plasma reactions, and this is why we can deposit films at very low nominal temperatures of from room temperature up to a few hundred degrees C. Nevertheless, because of the very high electron temperatures available, we can produce films of very good quality. Now, the most important applications of plasma CVD is for the deposition of nitrides and oxide layers. Let us have a look at the plasma type, the kinds of plasmas we are concerned with here. Plasmas, of course, are extending from a very large range, as shown here, in terms of electrons per cubic centimeter here, as a function of the absolute K times T in electron volts, the temperature. You can see that you have many types of plasmas that are formed. We are interested in this case in the range of the glow discharges only. We are not, even though other types could be used, but these are the ones that are commercially used for the deposition of films. Now, another aspect is, another reaction type, shall we say, another technology really is photo-CVD. And here, the principle of reaction is the selective absorption of photonic energy to initiate deposition processes. In many cases, mercury is used as the transfer agent of energy. mercury vapor is used as the photosensitizer, for example, for certain gas-phase reactions. In this case, a mercury resonance lamp is used, which operates at 2537 angstroms to serve as an irradiation source to activate the mercury from the ground state to the excited state, which then transfers energy by collision to reactants in the gas phase and producing various types of films. Very simply listed are here the formation of a silicon of species that will produce the silicon nitride. We have mercury in the ground state being activated to excited mercury, which then interacts with silane to produce a silyl radical and a hydrogen radical, and it goes back to mercury in the ground state. In other words, the mercury really acts as a catalyst, which is not consumed, it's regenerated. And again, down here, the mercury now will again be activated and produce a radical with ammonia here to ammonia type radical, which again going back to the ground state. And the various species now, of course, interact, finally forming silicon nitride. Of course, there are many more steps involved in that type of reaction, but which are quite poorly understood at this time. Now, the advantages of photo-CVD are listed here. We can use low temperatures of the deposition, such as 50 to 300 degrees centigrade at a pressure range of 0.3 to 2 torr. We avoid charged species, which is one of the main advantages, which is the case in plasma. For example, we do have charged species, that is, we have irradiation effects. We have excellent step coverage that results from photo-CVD, low pinhole density in the films, loose particles, and so on. And we can, because of the low temperature, we can use this type of process for the deposition even over plastic materials, which could not be done readily by any other means. There are some disadvantages that are listed here, namely the deposition rate is somewhat low compared to atmospheric pressure CVD. It is okay compared to LPCVD. It's about 150 angstroms per minute, which is reasonable. Nevertheless, the mercury contamination, of course, is one aspect. We do get some mercury trapped in the films, even though we have very small quantities, maybe 10 to the 16th or less. But it is a definite disadvantage for use of this type of reaction for CVD applications in VLSI. There are ways to get around it. We can use different kinds of reactants that are more sensitive, such as disilane, for example, or we can use a higher frequency type of ultraviolet that is more intense. But there are problems still associated with that type of process. Now, a related process is laser CVD, which is really also a photo-CVD process, and that's outlined in the next slide here. There's really three types of laser CVD. It's pyrolysis, evaporation, and photolysis, depending on how the reaction is done. In pyrolysis, very simply, we have a local heating effect. We use the laser to selectively heat the substrate, and then at that site, chemical reactions will take place to build up a film of desired composition and thickness. So we really use this as a heating source, essentially. In the case here of evaporation, we use the laser to, in this case, we use a very high flux of photons that is directed on the target and essentially evaporates material from that surface, transferring it to the substrate. So that is another way of using the laser. The third type is photolysis. In this case, it is very similar to the photo-CVD reaction I just discussed a moment ago here. In this case, the laser is absorbed by gaseous reactants in a single or multiple photon type process, and the absorption then leaves donor molecules in the excited state that can interact, and by products of the photodissociation then will lead to new kinds of films. This is perhaps the most interesting type of process here, because we have to select the wafer, the laser wavelength to match the reactant species. So they have to be tuned up. If that is achieved, then you have a very selective reaction, so that there are no other side products, no other side reactions taking place except for that one specific reaction which proceeds. So you have the possibility here of doing a very selective and very highly controlled type of reaction. So far for the basics. Now a few words about reactor systems. Essentially, we can divide the reactor systems here into, as shown here, into low temperature reactors, namely those operating at a temperature below 500 degrees centigrade. And those are the horizontal displacement type flow reactors used in industry widely for the deposition of oxide and glass films. We have vertical reactor systems which operate on a batch type operation. Let me just go down the list here. Horizontal displacement flow reactors, or the vertical rotary batch reactors. These are the relatively simple type of hot plate reactors where a batch of wafers is deposited, is positioned, and then is deposited on. So the next one here is the continuous production processing system, such as the various types of conveyor belt type of systems where the substrates are going into the reactor on a heated conveyor belt, so to speak, and are being coated with the material. In most cases, those are open to the atmosphere. That is, they are used under atmospheric conditions, and are rather than LBCVD, the APCVD systems will be used. And that, of course, is especially useful for the production of oxide films, silicate glasses, and that type of application. We then have the high temperature reactors, those operating at beyond 500 degrees C. And we have here the hot wall tubular and bale types, or the cold wall tubular bale types, and also the what we call pancake types. Now the second types here, the cold walls, are used for epitaxy, for example, at high temperature for the deposition of elemental semiconductors. Then, of course, we have the LPCVD reactors here operating in at a low pressure range, low pressure hot wall systems, and low pressure and high temperature hot wall systems. Depending, again, they are divided into these types, two types, because there is a difference between the gas introduction for low temperature hot wall systems and the high temperature ones. In all cases, however, we have a hot wall type system where the entire system is isothermally under isothermal conditions. And then we have the plasma promoted reactors, which of course are in a way all LPCVD reactors, producing materials at low temperature. So this is why I call them LPCVD reactors. We have two types: the capacitively coupled parallel plate reactor type and the inductively coupled continuous processing system, which both of these have been used. The more important ones, however, are the types based on the capacitively coupled parallel plate reactors, which can be rotary type radial flow reactors, or they can be tubular types where the wafers are standing up, similar to LPCVD reactors. This is a typical tubular type LPCVD system. If we look at the diagram here, we can see that the heart of the reactor is the tube here, which is essentially a diffusion type quartz tube where the wafers are standing up vertically in bolts, spaced in distance of a few millimeters to a centimeter or so, depending on the reaction that's going on. Now, the latest type of CVD systems of this sort may have a capacity of 100, 200, or even more wafers of the size up to 3, 4, or 6 inches even. And what we can see is that the gases are coming in, they are metered here, coming into the system. There's a pressure gauge up here to control to tell us the pressure of the reactor itself. Pass through the tube here and finally exit through the end here, where we have, first of all, a particulate filter to eliminate any type of contaminants before so they don't get into the pump. Here we have a mechanical booster pump here, and a rotary piston pump, which is a typical mechanical type pump. And we also have a configuration here where we have a dry nitrogen inlet that allows or that prevents back diffusion of oil from here into the system. So that's a very typical type of system. Now the LPCVD can be modified in a way, as I said, to have plasma capabilities, in which case we have the plasma reactors, tubular type plasma reactors. Now one other type of reactor we like to have a look at before we finish this segment here is the photo-CVD reactor. In this case, we have, first of all, we have the wafers located as shown here, with the wafers are being heated to a temperature of perhaps 100 degrees C or so, 150 degrees centigrade. And gases are introduced, in this case, through over the surface of a mercury bubbler. This is sufficient to pick up enough mercury vapor to react in the gas phase. So usually some or all of the gas is passed through here. There's some mercury here in this container. Enough vapor is picked up by the gas to introduce the mercury into the reactant space here. And in this case now we have a fairly closed space situation where we have a quartz plate close to the substrate surface, and the ultraviolet lamps positioned above here in as close a proximity to the substrate as possible. That will now produce give us the radiation needed to have the reaction taking place. And after the reactions have been completed here, the gas passes, as shown here by the arrow, passes down the tube through the exit. And that's essentially, now we don't have any production type reactors available as yet based on that system, but there are several plans by several companies to remedy this, and shortly we will come out with a production system that hopefully will meet the demands of large throughput and controllability and so on, which we don't have available as yet. In the last slide here, we have a view of a typical laser type of CVD system, where we have as we can see, we have two types of reaction possibilities. We can have a surface reaction taking place by the laser coming in vertically from above, going through a number of optical filters and so on, to hit the substrate, in this case a silicon substrate, which would be normal to the incident of the laser. On the other hand, we can also have the laser coming from the left side, that is parallel to the substrate, in this case from the left going to the right, and the gases would be passed, as you can see, would be passed over the surface of the substrate and be reacted. So we have these two types of configurations. And perhaps the last slide here, we can have a look at the laser chemical CVD. We have a CO2 laser at typically 20 watts going through an attenuator here, power meter, shutter, and so on, all the way to the cell where the reaction takes place, which is shown down here. And you can see the laser beam coming to the surface, heating selectively the surface of the substrate, and the reaction will take place here. If the reactants themselves are indeed transparent to the laser. If they are not, then we have a reaction taking place in the laser, in the reaction volume itself, and then of course that would be the other type of photo-CVD. Okay, in the second part we will discuss the various types of films that are deposited by CVD and show you some of the processes involved in that. This is the second half of the lecture on CVD. As you remember, the first half we covered essentially some of the fundamental principles, the CVD processes and technologies associated with CVD for VLSI as we need them today, and had a brief look at the reactor systems. We are now proceeding to the second part, which is the deposition of specific materials. Here I have taken the oxides, silicates, and nitrides as the most important example for dielectrics. We'll then look at the CVD of some of the semiconductors, in which case amorphous and polycrystalline silicon will be discussed. And finally, we'll go to the deposition of conductors. And here I have selected aluminum, tungsten, and silicides as the most important ones. And then at that point, reach finally some all-over conclusions for CVD in general. Now, the insulators are listed here. Some of the important reactions for insulator materials are listed here, and we'll go down this list here. To begin with, silane with oxygen in the first equation at a temperature in the range of 300 to 500 degrees centigrade would lead to films of SR2 and hydrogen, in some cases water vapor as the side product. We can also use the reaction shown here, the second one here, using the organic starting material, the TIOS, or tetraethoxysilane, which can be pyrolyzed at a temperature of typically 740 degrees C in the presence of nitrogen or argon as diluent to produce a very good type SR2 film and some water vapor and gaseous organic side products that are eliminated. We can also use the halides, such as shown in this case here. We can use the silicon tetrachloride with water vapor, typical reduction reaction to produce at a high temperature of 1200 degrees centigrade SR2 and HX plus CO as the side product. Alternatively, we can go to plasma reactions where we have the silane reacting with nitrogen or with ammonia to produce silicon nitride type polymers. In this case, plasma nitride, which would be deposited at a temperature of in the range of 250 to 500 degrees centigrade. The typical type of LPCVD reaction is shown here, where we have ammonia and silane interacting to produce silicon nitride in a temperature range of about 750 to 1000 degrees C. Alternatively, we can use the chlorides, the silicon tetrachloride ammonia reaction, which will also produce silicon nitride of slightly different properties than the other type of reaction at a somewhat higher temperature. Or we can use the type of reaction shown here. We have an isopropoxide very similar to the TIOS number 2 reaction. Here we have aluminum isopropoxide at a temperature of 420 at atmospheric pressure with some oxygen that assists the pyrolysis, leading to aluminum oxide films of very good quality. Or we can use a high temperature reaction, which is shown down here, aluminum chloride and the reduction reaction, the reaction with hydrogen to produce aluminum oxide and the HCl and CO. However, we do have to go to a high temperature, like typically 900 to 1200 degrees centigrade. On the bottom, I have shown two types of reactions which are quite important, namely the application of the hydrides for doping applications, that is for production of doped oxide films or silicate glass films. In number 9 there, the first reaction, we have silane mixed with phosphine and oxygen as the oxidant at a temperature of 300 to 500 degrees C, leading to phosphosilicate glass, which is a combination of SiO2 plus P2O5. However, it's not a mixture, it is a chemical compound. That is, we have formed now a silicate glass bond, which is different from just a mixture of the two oxides. It's quite a compound, a new compound in itself. If we use the diborane instead of the phosphine, then we produce a borosilicate glass or boron-doped oxide if the concentration of boron is low enough. If we combine the two reactions, we can produce BPSG or the borophosphorsilica glass, which we will discuss in some more detail. If we look at the various types of glasses that are available that can be made by CVD, we can see them listed here. The oxides, many types of oxides can be produced quite readily. We have, of course, the SR2, aluminum oxide, and so on. All of those can and have been done by CVD techniques. The oxide, the SR2, of course, being the most important one. Going to the binary silicates, here we have the PSG, BPSG, the phosphosilica glass and the borosilica glass and the arsenosilicate glass. Those perhaps are the most important ones. There are other ones we can produce, for example, aluminosilicate glass, lead silicate glass, and zinc silicate glass, but they are not utilized commercially. We then have the ternary glasses, of which the BPSG is the most important one here, and that's the borophosphorsilica glass. Alternatively, there is also a possibility that we can use germanium instead of boron, instead of phosphorus, and produce a germanium borosilicate glass. Of the nitrides, the silicon nitride here is, of course, the most important one. The high temperature stoichiometric SI3 and 4, and also the plasma nitride deposited at a lower temperature in the plasma type systems. And then, of course, the oxynitrides, which are mixtures of with oxygen, essentially mixtures of the oxides with the nitrides, where the silicon oxynitride is the most important one. If we look at the reactions occurring in the formation of SR2 from silane, we can list them as shown here. We start off with the initiation reaction with excited oxygen radicals that form the silyl radical as indicated. Now you can see that the simple reactions I showed you to begin with are really a lot more complicated than the summary equations would indicate, because we have a series of free radicals forming which then interact, and in a whole sequence of interactions finally produce the desired product. Now the next step after this initiation reaction, in this case, we have a branching type of reaction which forms a number of intermediates such as SiHO compounds. And that's shown here, where we have the silyl now reacting with oxygen to form the SiH2O and oxygen, as well as the interaction of that intermediate then with additional oxygen to form to give us additional SiH2O2. And after this type of branching reaction, we will have a regeneration reaction and also a terminating reaction, where the product formed in number 2 interact with additional oxygen to, at this point, form SR2 and water vapor. And the interaction takes place as expected on the substrate of the silicon itself. That is, usually an adsorption of oxygen on the substrate surface, which then interacts with the intermediates formed in the as shown above. Now the overall reaction is shown here, which is of course very simple, but as we see, it is in fact extremely complex. We can have two types: either the silane oxidation leading to SR2 and hydrogen as the byproduct, or to water vapor as the byproduct, depending on reaction conditions. At atmospheric pressure, for example, we have both reactions taking place. LBCVD tends to give us the second reaction, primarily water formation as the side product. We can so then summarize here and say that a silane gas phase reaction to produce SR2 can really be defined as a thermally activated, surface catalyzed, but oxygen inhibited free radical heterogeneous branching chain reaction. And this puzzling thing here with the oxygen inhibition, we will see in a moment what is meant with this, because if we have too much oxygen present, then the reaction will be impaired, or in fact can be entirely stopped. if we look at the deposition of phosphosilicate glass films, which are produced from the silane, and phosphine, as indicated up here, at the ratio, silane-phosphine ratio of 20:1 in this case, diluent using the diluent of nitrogen, and a gas flow rate of 11 liters per minute. This is all done at atmospheric pressure. Essentially what we can see is, and of course what we do is we interact here silane plus phosphine with oxygen to produce the PSG. And the reaction I just showed you for silane is, of course, part of this whole reaction sequence. Now, if we look at the what happens here, the temperature of deposition here, how it affects the film deposition rate, which is shown, the vertical bars are the film deposition rate in angstroms per minute, whereas the bottom line here will show you the deposition temperature going from 350 to 400 to 450, and then the ratio of the oxygen to hydride, that is oxygen to silane plus phosphine ratio. And what we can see is for three temperatures, three-dimensionally now, what we can see is the behavior, namely that, first of all, there is a maximum in each case, as we can see. And of course, with the temperature, as the temperature is increasing, the rate of deposition increases, reaches a maximum, but then declines. And at the next higher temperature, as expected, you would have a higher deposition rate, and so on. The interesting thing here is that the deposition maximum occurs for different temperatures at different ratios of the oxygen to hydride. So if you go to a low temperature of PSG deposition at atmospheric pressure, then in the case of 350 degrees C, for example, you have to use a ratio which is perhaps 10:1 or thereabouts to obtain the maximum. That is the maximum in the rate, which is also the optimum of film preparation. That is, the best properties are obtained by this type of reaction. And of course, if you go beyond that, then you rapidly lose deposition rate, and you are wasting gas and also produce a film of inferior properties. And the same holds up here. As you go higher in temperature, and you have to increase the ratio of the hydrogen, or of the oxygen to hydride, in order to achieve a maximum and hopefully work on a plateau region here. Now, just to see, to make sure that this is not a peculiarity of the particular deposition system that was used, I have taken literature here from the literature and plotted them, superimposed them, and in fact, in this case, now these data here are from the Japanese report, where they did a similar kind of thing, and I plotted the data the same way, and you can see, in fact, we extend them to 300 degrees C, and you can see that the same behavior takes place almost quantitatively. In other words, even using somewhat different conditions, different reactor types, and so on, still will produce the same type of configuration. And that is a very clear indication of the oxygen inhibition if we have too much oxygen there, which holds for the silane oxidation for oxide, as well as the doped case of the PSG. If we look at the same kind of data now, but looking in terms of composition rather than the which is shown over here, rather than the deposition rate. The deposition, the composition in terms of phosphorus contents is shown in the vertical bars. And very briefly, we can again see what happens here. In this case, the solid data are the ones we generated in our own laboratory at RCA. The dotted ones are the ones from the literature. And you can see again, we have a similar kind of behavior. In this case, as the temperature is increasing from left to right, you can see we have a decrease in the film concentration of phosphorus. That is, as the temperature goes up, the phosphorus concentration goes down. As the deposition temperature increases, the phosphorus content decreases of the film. And that has mainly to do, in this case, with the high vapor pressure of P2O5, which is the intermediate that's formed in the process of oxidation of the co-oxidation of silane and phosphine. Okay, so far for that. So we have to be very well aware of the effect of temperature, that we can, if we change the temperature in many of these processes, it is not simply a matter of changing the rate of deposition. We may change the composition of the film, and we may have other effects that have to be kept in mind. Now, if we go a step further and mix the silane and phosphine with diborane, so we have a ternary glass composition, we now can produce ternary glass films, which we call the BPSG or the borophosphosilicate glass. And I'm illustrating these types of reactions here because of the importance of BPSG in VLSI applications. The first one is the one I just noted here, namely the use of silane diborane phosphine with oxygen in a nitrogen diluent at a hydride ratio of typically 40:1. This, at a temperature of 360 to 430 degrees centigrade, at normal pressure, will give you a very good quality of BPSG films. Typical deposition rates in this case are in the order of perhaps 1,000 to 2,000 angstroms per minute. They can be increased very easily, but then the film quality tends to deteriorate. You get more contaminants, particulates in the film, and generally we prefer a rate of about 1,500 angstroms to be about ideal in production reactors using atmospheric pressure CVD. Now, we can also use low pressure CVD as indicated here. However, if we remain with the hydrides, we have a problem because it is difficult to introduce, that is, the diborane is very reactive, tends to pyrolyze as it gets heated. And so we have to use some special type of configurations. Now, a very good way to do it is the use of a isothermal vertical force convection type reactor, such as an anicon reactor, which now produces BPSG films by the same chemistry as we use under atmospheric pressure conditions, except that we have to change the oxygen to hydride ratio to 1.5:1 typically. And that would operate at a temperature of 400 degrees C at about 0.2 torr pressure. Now, if we use a regular tubular type of CVD reactor, there we have the difficulty with the pyrolysis of the diborane because it's introduced into the reactor tube itself separately in a separate line and tends to pyrolyze. So it is difficult then to get enough diborane into the gas phase to make the reaction effective. So as an alternative then, or as a substitute, we have to use the boron dichloride as a substitute for diborane, this is more thermally stable and allows us to introduce that into the stream under the conditions shown. However, the problem here is that we now have some residual chlorine film in the film, chlorine contents in the film. Typical concentrations are perhaps 0.5% of chlorine, which has potentially deleterious effects in applications that involve BPSG and higher temperatures. So there is a special case here. We can use it, but we have to be very well aware of the presence of the chlorine. We can also use organic type systems combined with LPCVD. In this case, we have the TIOS mixed with trimethyl borate and either trimethyl phosphide or trimethyl phosphate, or the phosphine as an alternative, mixed with oxygen as the oxidant to give us a BPSG at a temperature in the range of typically 620 to 680 at a half torr pressure. And here we can use essentially a LPCVD reactor, which is modified for this particular application to some extent to give us the maximum or the optimum gas phase distribution. And finally, we can produce the BPSG by hydride chemistry, very similar to the ones listed above, using a plasma reactor. In this case, we would use a ratio of nitrous oxide, we would use nitrous oxide rather than oxygen as the preferred oxidant species. The ratio of the combined nitrous oxide plus oxygen would be about in the range of 35:1 to 40:1 at a temperature of about 380 degrees centigrade. However, there are many problems involved with the plasma CVD type of BPSG, and I would not recommend it unless you have some special applications or special use for it. But this is a good illustration of the variety of different techniques that are available for the production of a particular type film. Now, we have a look at some other types of films, or at least films done by different techniques. To begin with the plasma oxide, which is really a low temperature SR2 that is especially well suited for the deposition or aluminum metallization, where the temperature has to be kept very low. With very low temperature, I mean something like 300 degrees C or even less, in order to avoid or eliminate recrystallization of aluminum and the formation of spikes and shorts and that kind of thing. Now, listed here are a number of factors. The films produced have high breakdown strength, have good dielectric properties, and kind of meet the requirements that are needed for applications such as interlevel insulation between aluminum. Also, they do have some hydrogen, but the hydrogen tends to diffuse out very readily since the films are permeable to hydrogen. Deposition conditions are listed here. We use typically silane and nitrous oxide, or as an alternative, nitric oxide, CO2 or oxygen. Any one of those, but generally nitrous oxide is probably the most frequently used oxidant species. The reaction is taking place, is shown there with, again, a summary reaction that looks very simple, even though it is really quite complex. But okay, the temperature range is 250 to 350 degrees centigrade, but the temperature, of course, in plasma reactions is not the primary thing. It's the plasma that drives the reaction, so that the temperature increase or the supply temperature is really only utilized to produce better film qualities, like better, higher density and less gas absorption, that kind of thing. Now, typical compositions here, or properties of the films are indicated here. The film is SiO2, but strictly speaking, it has a small amount of nitrogen or silicon nitride included in it. So there are a few percent of nitrogen, so we can really say the most exact description of this type of film would really be as a silicon oxynitride, even though it is predominantly SiO2. The films are conformal, they are crack resistant, practically pinhole free, and with very good breakdown voltage and dielectric constant as shown, and also refractive index, indicating that the quality of the film is indeed quite high. The stress, of course, is in most cases compressive, and that's another good feature. It is on the 1 to 2 times 10 to the 9 dynes per square centimeter compressive, which is a very good level that is desirable. And the gas inclusion is shown down here, 2 to 9% atomic hydrogen and some nitrogen, which, however, produces no problem in its application. Now, the second type of film produced by plasma reactions is the plasma nitride, and this is certainly probably the most important one of the nitride of the plasma films. And again, it was the first material that was deposited by plasma techniques and really got things going in the whole field of plasma deposition, because the nitride deposited by plasma reactions can be done at a very low temperature and still has properties similar to the high temperature nitride, namely protection against sodium ion diffusion. And so that, of course, is the main application of these films. As indicated here, the low temperature of deposition allows the use of aluminum metallization, which would be impossible if we would use the high temperature SR3 and 4 type nitride. And also because of the compressive stress in the films, it is possible to build up layers to a thickness of a micron or 2 microns even without cracking. And just like the high temperature nitride, plasma nitride is an excellent diffusion barrier against moisture and alkali ions, as I had already mentioned. And the reaction conditions are listed down here. We can use either silane and ammonia or silane and nitrogen as the nitrogen compound or nitrogen source. The reaction is indicated there. If we use nitrogen, it is more difficult to dissociate a nitrogen molecule than it is to dissociate the ammonia molecule. So the reaction, the rates of reactions are lower, deposition rates tend to be lower. And as a result, one prefers in practice the use of ammonia as the source of the nitrogen. And temperature, as I said, temperature range is not critical. Pressure of 0.2 to 3 torr is used in that range. And deposition rates are typically 300 to 500 angstroms per minute, depending on reactor systems. The variables, of course, will vary from system type to system type. But the typical film properties are summarized down here. Again, just like the oxide, plasma oxide films, they are conformal. These are conformal, hard, crack resistance, nearly pinhole free, with very good breakdown strength and a dielectric constant of about 7 and an index, effective index of 2.0 to 2.2. And the stress, as I indicated, is typically compressive. However, there is a variation depending on the type of frequency used for the reactor. In the range of 25 to 450 kilohertz, the stress is typically in the range of 4 to 8 times 10 to the 9th dynes per square centimeter. Compressive, very compressive, more so than we would like to see, because that will cause problems later on in its application. If we have a frequency in the range of 13 to 56 megahertz, then the stress can be compressive or tensile, and we observe it as essentially zero stress at approximately 2 megahertz. So as you can see, the properties of the film, especially stress, is dependent on certain parameters. Frequency is only one, but there are other ones that are determining the type of stress one will obtain. Gas inclusion here, of course, is mainly the hydrogen, which may be from 15 to 30% bonded to either silicon or nitrogen. And of course, that will produce a problem of outgassing later on, which may produce blistering of the film and effects on device performance. So that hydrogen is a very undesirable situation in the case of the plasma nitrides. So far for the dielectrics. And we now have a look at the semiconductors. And of course, semiconductors really is a whole range. We should really consider elemental semiconductors as well as the compound semiconductors. But in this particular presentation, we have to essentially concentrate on the elemental ones here, because there just isn't enough time to cover all this kind of material. So let's have a look at the type of the reactions that can be used for the production of silicon and also germanium. And to begin with here, we have seen that reaction before a few times already. Thermal dissociation of silane in a plasma discharge can produce amorphous silicon at a very low temperature, like 200 to 300 degrees centigrade. Or we can use the reaction listed here, the simple type of dissociation of pyrolysis reaction at 800 to 1000 degrees C to produce heteroepitaxial silicon. That is silicon that would be produced, for example, on sapphire, where we cannot use reactions containing chlorine that would attack the substrate. Here, in this case, where we have a silicon substrate and want to produce a homoepitaxial film of silicon, we can use the chlorosilane, such as the tetachlorosilane, or the trichlorosilane or the dichlorosilane. Any one of those silanes can be used to produce epitaxial films of silicon. The germanium species are analogous in principle to the silicon ones. Germane reacts just like the silane would generally at an even lower temperature, and the germanium tetrachloride again can be used for the production of germanium epitaxial layers very readily. So this gives you a kind of a very brief overview. Now let's go to the ones that are perhaps the most important ones in terms of VLSI applications and have a closer look at these, namely the amorphous and the polycrystalline silicon types. I have listed these kind of the key features in each case here. The growth mode of the film formation depends very much on deposition conditions. Namely, the amorphous type of film from silane or also from disilane pyrolysis is favored generally at a moderate temperature in the range of about 550 to 580 degrees centigrade. And in this case, the film growth rate is much smaller, is much larger than the surface mobility of the atoms at the substrate surface. So as a result, you have an amorphous type film forming. In the second case here, LPCVD of amorphous silicon has low growth rates, primarily because it is an LPCVD reaction. But if followed by recrystallization, nevertheless has advantages in the control of polycrystalline structures of the film and the formation of even epitaxial silicon films on insulators if you go to high enough temperatures. So even though the rates are low, there are definite advantages using LPCVD for polysilicon formation. Now the plasma-enhanced CVD or plasma-assisted type of CVD for silicon deposition will produce a hydrogenated amorphous silicon, which is produced at fairly high rates and is produced at low temperatures. Now in this case, the hydrogen contents vary strongly with plasma conditions, reactants, and other factors, but especially the temperature. Again, as the temperature increases, there is less hydrogen being included. Now, of course, this type of film is used for photovoltaic applications primarily, where the hydrogen is, as an exception now, is a beneficial effect. Namely, it will passivate dangling bonds and so on, and produce very desirable effects in solar cell applications, for example, where the plasma silicon is used, amorphous silicon is used very widely. Now, the grain structures of films deposited from silane varies from nearly amorphous to very large grained polycrystalline, depending on the temperature conditions, deposition rates, annealing conditions, and so on, and also the reactants. In general, a temperature less than 575 degrees centigrade yields an amorphous deposit, while columnar structures in the range of 0.03 to 0.3 micrometer sizes result at temperatures above 625 degrees C. So, as I said, the temperature is an extremely important aspect for forming specific types of silicon films here. Now, if you go to very high temperatures, such as 1150 to 1420 degrees C, and low growth rates, assuming you have a clean substrate surface, atoms rearrange very rapidly compared to the growth rate, that is, in the structure that's being formed, and then which will then result in the single crystalline formation of silicon films. Now there is some more here on the polycrystalline silicon, both undoped and doped. And what we can say here is the polycrystalline films, as deposited in the intermediate temperature range, well, that's what generally is done. They are deposited in the intermediate temperature range, and they are obtained at fairly high growth rates. They crystallized when heated, but the crystallization temperature depends on the impurity levels in the films, so we cannot make a general statement here. The second point here is the silane in nitrogen or hydrogen and the dichlorosilane in hydrogen are used generally as the reactant species, mainly for applications in thin film structures. Now, this dichlorosilane is used for thick film applications, where we have essentially intrinsic polysilicon that acts now as an insulator. And the high temperatures or large partial pressures of the reactants lead to gas-phase nucleation, especially in the silane system. So we have to be very careful to avoid that type of defect formation. The all equations of the formation of silicon from silane and dichlorosilane are listed here. And okay, now the LPCVD of polysilicon from silane at 600 to 650 degrees C at 0.3 to 0.6 torr pressure generally leads to a very good film uniformity, that is within 5% variation, and growth rates of approximately 10 nanometers per minute. The polysilicon films from silane are all of these can be deposited or can be doped in situ by the addition of diborane phosphine or arsine in hydrogen. However, the dopants strongly affect the growth rates and the film uniformity. So we have to be aware of that. And the effect is indicated in some more detail down here. We observe an enhanced growth rate in the case of diborane doping. And this is most likely due to a surface electronic effect. The decreased growth rates which we observe with phosphine and arsine generally are due to surface poisoning, and it is believed some species of pH sub X and ASH sub X species are involved in doing this. The large non-uniformities in this case are caused by the rapid disilane or silane or SiH2 chemistry, which is initiated in the gas phase, as we saw previously in one of the previous slides. Okay, we have just one quick look here at a plot which gives you an idea of the growth rates we observe here. This is the film growth rate here as a function of temperature, using silane as the species for a reaction species. And we have two curves are shown here. They are typical Arrhenius type plots, one with an activation energy of 32 and one with 39.9 kilocalorie per mole. They are well behaved, but the difference here is essentially adsorption of hydrogen side products which influence the exact reaction rate of the film formation. Typical deposition rates, as you can see, are in the range here of about 100 angstroms per minute, and of course we have the temperature range here is used for the amorphous type film up to about 580, and the higher temperatures are used for the polycrystalline film formation. Well, I think we'll go right on to the conductive materials at this point, because the third type of material we are concerned with is the deposition of conducting materials by CVD. I don't think I have to stress the importance of conducting materials in LPCVD, in VLSI applications. We can deposit both elemental metals and alloys, and as I had mentioned before, tungsten and molybdenum are particularly attractive because they are difficult to deposit by physical means of deposition. Also, the refractory metal silicides have become very important, and they're listed here. And there are other compounds like transparent conductors, which are really non-stoichiometric oxide semiconductors, such as tin oxide. Again, they can be done by CVD very well as superconductors like niobium tin and so on. And then, of course, there are other materials that are not used in VLSI, but that can be readily formed by a number of CVD reactions. Okay, now the aluminum here, in the past, aluminum, or even up to this point, aluminum is deposited for VLSI applications primarily by sputtering and evaporation, and also by physical methods. However, the use of LPCVD has been optimized because there are some definite advantages using CVD rather than deposition methods based on physical principles, mainly because of the feasibility here to obtain conformal coverage of the structure. Now, if we do that, we can have a look at this type of reaction that's listed here. We start off with an organometallic. Mainly in the past, so far, we have used tri-isobutyl aluminum, which dissociates in a temperature range of 200 to 300 degrees centigrade to elemental aluminum and side products which are swept out of the reaction chamber. As a secondary step, once we have the aluminum, we can now dope this with silane at a temperature of about 460 degrees C to produce a silicon aluminum alloy, which is the usual preferred type of aluminum used in silicon IC applications. Details are listed here that have been published so far. This reference goes back to Cook from Solid State Technology, but it gives you it's a good example of what the reaction in principle at least looks like. The aluminum source temperature is 140 degrees C to produce enough vapor that can be introduced into the system to produce the aluminum reaction. Perhaps the most interesting aspect is the nucleation here. We do have to introduce some species of reactive material that nucleates the films. In this case, we use titanium tetrachloride that is introduced into the system and passed over the substrate and now forms nuclei from which aluminum growth takes place. If we don't do that, we get island formation and we get very irregular growth of aluminum. So this type of exposure now ensures a uniform nucleation. Now the aluminum deposition temperature is typically 260 degrees centigrade at the rate of 100 to 200 angstroms per minute. Generally, the uniformity is at this stage of the game not too good, but a great deal of improvements have been achieved in the last few years now, so that eventually this process will be introduced into large-scale IC manufacturing. There's also still some problems with the roughness of the surface that is not as good as it should be. The best or the greatest advantage, of course, of the whole process is the conformal coverage of the, as indicated in number 11. The final composition of the film in this case is about, ranges anywhere from 0 to 0.8 weight% silicon in pure aluminum after the doping is done with silane as indicated up here. Okay, now we have to look at the tungsten. And this has been tungsten. There's an intense amount of activity going on around the world on tungsten deposition. And again, one would think it shouldn't be that difficult. In principle, the chemistry is rather simple and seems straightforward. But to realize a process that is working in production to the kind of reliability we need and controllability, additional work is needed. But let's have a look here at the two reactions. One is a selective deposition of tungsten by reduction using the silicon substrate itself. Now the reaction is shown on here, and we use the tungsten hexafluoride reacting with silicon to form tungsten metal and SiF4, which is given up in the gas phase. And the gas mixture typically is 1 volume of the fluoride to 50 volumes of argon. Temperature is typically 300 degrees C, and it's very sensitive to it's a very important variable. If you go much beyond that, then you begin to have non-selective depositions. The tungsten tends to deposit not only in the silicon areas, but all over the structure of the oxide-coated substrate. which of course may be desirable later on if we do want a continuous film that is non-selective. But if we want selective deposition, we have to be very careful both with the temperature, with the dilution, with the rate of deposition, and all the finer points in the CVD reaction to produce really films that are confined to a particular area. Now the thickness is limited to about 100 to 150 angstroms of tungsten, as indicated here, because after that there is no more silicon available for production, for the reduction of the tungsten hexafluoride. So you will finish the reaction itself at that point. However, you can continue the reaction by now introducing hydrogen to the mixture. And the hydrogen, of course, now acts as the classical example of metal reduction from the fluoride to produce tungsten by formation of HF vapor. However, the reaction is still, for some time, still can be continued as a selective reaction. Namely, a preferred reaction is still taking place on the tungsten, which we formed here. In other words, we can build up this thickness here with using this process to an additional level, so that because the deposition is preferably taking place on the tungsten itself. In this particular case here, however, I have shown the non-selective deposition, namely when you want to cover the entire surface of the substrate, that is the SiO2 as well as the already coated via areas. And so by judicious choice of the reaction conditions, we can then produce a film that meets the requirements for high temperature intermetal metallization systems. Let me just backtrack for a moment here, and I have a summary here of the silicides, because I think that will be kind of give you the... of course, the CVD of silicides offer formation by CVD is considered superior to the physical methods of deposition, such as sputtering, evaporation, and thermal reactions, for a number of reasons. Now, films with good adhesion can be obtained, excellent step coverage is secured, and the structure of the film itself can be controlled with very excellently, very good, can be kept under very good control, shall we say. Now, the CVD processes so far available for silicide formation are essentially titanium disilicide, the tungsten disilicide, tantalum disilicide, and a few more, but perhaps the ones that have been most developed to the greatest extent are the ones listed here. Now, if we have a look at the tantalum silicide in the slide shown here, this is one way we can produce tantalum disilicide, namely the deposition of a polysilicon layer first at a temperature of, say, 615 to 635 degrees C to produce a polysilicon sublayer. Now, the temperature of deposition is in the range of 615 to 635, as indicated here, for the formation of the polysilicon sublayer. And the silane flow rate is also shown here, and some additional details. Once we have obtained a film of polysilicon sufficiently thick, we now switch over to the tantalum doping here. In this case, we use tantalum pentachloride here as the source material, which is kept at a temperature of 125 degrees C to obtain sufficient vapor pressure to get the reaction going. We also use hydrogen as the carrier gas for introducing the vapor mixture, the vapor into the reactor. In this case, the deposition rate is about 125 angstroms per minute. And what we wind up with is a composition of tantalum silicide, as shown here, which is not what we really want. But if we now interact, or if we give a thermal annealing treatment to the final structure, we can obtain exactly what we like, namely a stoichiometric film of a tantalum disilicide, which has the best type of the best conductivity, of course, and that's the kind of film we want. However, we do have to heat to a temperature of 1,000 degrees C in argon for, say, 30 minutes in order to obtain a 48 ohms centimeter type film. Nevertheless, the attractive feature of this type of process is that it can be done in the same reactor under very similar conditions, just by changing, by adding one additional component, namely the tantalum pentachloride to the silane mixture. Okay, now the tungsten disilicide or tungsten silicide formation is shown here. Again, we can use tungsten hexafluoride, reacting this with the silane to produce tungsten hexafluoride, to produce the tungsten disilicide and HF as the byproduct. In this case, the temperature of deposition is in the range of 330 to 370 degrees centigrade. Pressure is in the range of 300 millitorr or less. And deposition rates are typically 50 to 100 nanometers per minute. The interesting thing here perhaps to point out is that the rate dependence is directly proportional to the tungsten hexafluoride flow rate and is independent of temperature and pressure. There is one other strange aspect here, namely the effect of tungsten hexafluoride on the silane molecule itself. There is a good degree of evidence that there is a catalysis taking place, namely the tungsten hexafluoride catalyzing the pyrolysis of the silane to silicon, because otherwise we would not be able to run the reaction as shown here. So this actually helps in this case. Now the resistivity, to give you an idea of the kind of film formed here, the resistivity is in the range of 600 to 900 microohms centimeter as deposited, which can be reduced down to 30 to 60 microohm centimeter after annealing at 1,000 degrees C. Now, as far as conclusions are concerned, I have a set of some 10 points I'd like to go through very quickly here to summarize this. Now we'll summarize the whole CVD process. We have everything we had discussed in CVD. And as we have seen, we have CVD is a unique process. That is, we can form materials which we can not easily or not at all form by other methods of deposition, and especially doing this at a low temperature. I would say that CVD is absolutely essential for our space-age type solid-state technology we need for the formation of insulators, dielectrics, semiconductors, and conductors, films of very high purity, of the perfection and excellent compositional control that are now required. So it is an essential technology that is certainly here to stay. The CVD processes are essential. Essentially, we can say really surface chemical reactions if they are heterogeneous, which is what we like to see, of course, rather than the homogeneous type reactions. And in general, they follow the physical chemical laws of thermodynamics, kinetics, energy transfer, mass transport, and so on. There's nothing peculiar about the type of reactions going on here. The gas phase reaction here, however, is the competing type, homogeneous type of reaction, which must be controlled in order to minimize the undesirable effects, namely gas phase nucleation of particulates and particles that will be a source of contamination. So that is probably the weakest point of CVD, the most difficult one to control on a production scale. Now, the commercial CVD production reactors that have been designed cover APCVD, LPCVD, plasma systems, and so on, but they are not as yet available for the photo CVD, including laser CVD applications, which is something that will have to await the near future. Another thing, future developments in CVD technology are certainly in the perfection and the economic production type reactors and reaction systems that have to be developed for automated deposition of films with improved uniformity and the kind of structural quality and compositional control that's necessary. In point 7 here, processes for new materials, especially refractory metals and their silicides for VLSI applications will be developed and expanded to a much greater extent than we now have. So that's certainly the most immediate activity in CVD at this time. In the field of the metal organic CVD complex compound formation for semiconductor synthesis also will be rapidly expanded. And I had, unfortunately, no time to really talk about that, but this is a very rapidly evolving technology which is becoming quite important. As far as limitations are concerned, the fundamental limitations of CVD are essentially the reaction feasibility and the reaction kinetics that govern the CVD processes, and that's really about as fundamental as you can consider it. The technical limitations, on the other hand, are shown here. They include unwanted and possibly deleterious but necessary side products which are always present. And of course the ever-present particle generations, as I mentioned already, by the homogeneous gas phase reaction that must be minimized. So those are perhaps the limitations that have to be eliminated or at least solved to a better extent than we are now capable of doing. Thank you.